What I want to do with you about climate change is to open a discussion on its technical implications. I don't want to get into the politics of it, I don't want to get into the economics of it. I just want to try to focus on the technical level. And in order to focus on the technical level, we have to understand to what extent it has an impact on our design variables. Because this is the problem for an engineer. The problem for an engineer is when we have to make a design, to estimate the design variables, and we have consolidated approaches for doing that. You know how to estimate design variables for several applications. The problem is that in our case, the design variables are connected to climate. And if climate is going to change in the future, we have to take into account in our estimation of the design variables this change. So this is the kind of discussion that I want to undertake with you. First of all, we have to understand what is the reason for climate change, which is not easy. It's a problem in itself, because we know that climate has always changed. This is already a controversial statement. Climate has always changed, we know that, but we don't know the reasons why it has been changing and continues to change. We had glaciations in the past, we know that. And the reason, the physical motivation for glaciations is still unknown. We have some hypotheses on that, but we are not sure about the motivation of that. A possibility recently is that climate is now changing for the human impact. And so let's try to understand how this could happen. And this is a sketch of the greenhouse effect. The greenhouse effect is well known. It means that if we increase the concentration of greenhouse gases in the atmosphere, they are called greenhouse gases because they tend to establish a layer in the atmosphere which is like a roof. And this layer allows the solar radiation to come in and then to pass through it, but on the other hand, this layer blocks the return flow of heat from the earth. And that's like a greenhouse. Greenhouse allows the light and the solar radiation to come in, and then vegetation can grow up, but the roof doesn't allow the heat that is produced by vegetation, by the soil itself, to go out, and therefore you get an environment that is warmer. And the greenhouse gases are the same way. This is something that is physically understood, and therefore there is no doubt that if we increase the concentration of greenhouse gases, there is a greenhouse effect. What are greenhouse gases? The most known and the most important is CO2. And of course we know that human activity, but not only human activity, life and vegetation, they release CO2. But human activity in particular has increased the release of the CO2 because after the industrial development, so after 1800, beginning of 1800, we started burning fossil fuels, and therefore there is some carbon that is in the lithosphere, which we are burning for producing energy, heat, etc. And that carbon is transformed by burning in CO2. And this is one reason why we believe that the human activity may have an impact on climate, because burning fossil fuels created this kind of layer, and the layer promotes the greenhouse effect. There is to say that this scheme, which is very simple, it's not completely understood. So it's not completely understood what is the impact of human activity in terms of release of CO2 compared to other contributions, like natural emissions of CO2 from volcanoes, from animals, and emissions of CO2 from the oceans. The oceans emit CO2. They can store CO2 and release it, depending on the temperature of water. If the temperature of water is lowered, then the ocean tends to absorb CO2. If the temperature increases, the ocean has the capability to release a great amount of CO2. And the oceans cover 70% of the Earth's surface. So it's not yet clear what is the interplay between natural releases of oceans and human releases. Question?
Basically, the emission of CO2 of ocean is related to pollution.
No, it's not related to, it may be related to pollution, because of course if you increase the concentration of its CO2 in the atmosphere, the ocean stores more CO2. So it may be indirectly related to CO2, to pollution, but the real driver of release and storage of CO2 in the ocean is temperature. So let's suppose that you have an increase of temperature because caused by humans, and then the ocean reacts by releasing even more CO2, and therefore there is a negative feedback. Negative, meaning that you create an impact, and the result of the impact emphasizes the impact even more. But a driver of ocean surface is also solar activity. Solar activity has its own variability. It's variability in cycles. Some of them are known, Milankovitch cycles. You can look on Wikipedia, there is a link in this web page. And there are other cycles whose motivations are not known, and therefore if you have an impulse from sun and it causes an increase of temperature in the ocean, and the ocean reacts by releasing CO2. This is the reason why, like 5-6 millions of years ago, the concentration of CO2 in the Earth's atmosphere was much higher than today. So today the concentration of CO2 in the atmosphere is the highest starting from like 6,000 years ago. I'm just giving numbers, but I don't remember well. I'm not a climate scientist. So if you look back at the recent past, the recent meaning 10,000 years, we have the highest concentration of CO2 in the atmosphere. But if you go much further back, like 5 million years, then you find, and we found it through ice cores, where we had much higher concentrations. The reason may be volcanic eruptions, or maybe that there was a solar activity that was higher than today. Maybe. So, as I said, this mechanism then it's understood in its big picture, but the details are not well known. Also, what is not well known is the whole mechanism of the feedbacks. I already mentioned a feedback. Indeed, the Earth, nature, it has a stable equilibrium. It has to be stable, because if it was not stable, we wouldn't be here today. So nature is by itself robust. And the reason why it's robust is because it can react to shocks by establishing feedbacks. Meaning that if you have a shock that perturbates the equilibrium, the system is able to react to protect itself with a feedback. It's like our body. When we get an illness, the body reacts by producing, I don't know how to say in English, but by getting immune to the illness. And this reaction is a feedback. Just feedback is a return effect. Nature has this capability. And they give you an example. If you release pollution in a river, the river is able to use the oxygen that is dissolved in the water to dissolve the pollution, to eliminate the pollution. This is a feedback. And the Earth is the same, so we don't know really what are the feedbacks that the climate system can trigger in order to compensate, not to suffer from global warming. And I give you another example which is related to this. We think that with increased temperature, evaporation should increase. So the logic reasoning is warmer climate, more evaporation, more rainfall. And so our guess at the beginning, like 20 years ago, was that rainfall, evaporation should increase and rainfall should increase. Actually, if you look at measurement of evaporation over the world, there were studies, evaporation declined, it didn't increase. there was a slight decline. And the result is that if you look at rainfall series, on average, you don't see big changes. Why is that? We don't know, but a possible explanation, very likely, is that wind speed decreased. And because evaporation is conditioned by temperature, but also by wind speed. I'm not sure if I already said this 1 month ago, but I think it is a very interesting example. And therefore it means that the system was able to react. And in order to avoid evaporation, a possibility also could be that as soon as evaporation increases, you get clouds, and clouds lower the temperature, and therefore you reduce evaporation. This could be a possibility. So, meaning that what I want to say is that the whole climate system is still barely understood, and therefore it's not clear what is the interplay between these effects, impacts, feedbacks, etc. There are two ways to analyze the impact, to analyze the changing climate. One is inductive, like we look at the data, we look at past data, and we look at trends, tendencies, and try to extrapolate them into the future. This is an inductive approach. It starts from observation. There is also a deductive approach, meaning that we use a model. We build a model of the climate system, and through the model we increase the CO2 in the atmosphere. So we assume that CO2 concentration may double in the next 50 years. And then through the model we study the effect. These are two different schools of thought. The engineers usually they tend to rely on data. Scientists, researchers, usually they tend to rely on model. And there are reasons for doing this. The reason of the engineer is that, I really trust what I observe. And this is the usual approach by the engineer. We observe a phenomenon, we measure it, and then we design accordingly. Keep in mind that the engineer has a very precise scope, a very precise purpose. We need to design something, and we have to make sure that the design is robust, is efficient, is a good design. We cannot tolerate that a bridge collapses or an house collapses. So usually we tend to be very empirical, very to the point. The scientist is a different thing, because the motivation is to understand rather than designing. A scientist, a pure scientist, their motivation is to understand. And therefore, of course, the data to a scientist may look uncertain, because you know that in any measurement there is uncertainty. So the scientists usually prefer to start from the theory, from knowledge, from a model. Different school of thought. But the problem is that in this case you get different conclusions. So if you look at the climate models, you get a kind of prediction. If you look at what happened in the past, if you look at the data, you see that the prediction by climate models doesn't comply, doesn't agree with what we observe. And therefore, just be aware of that. And as an engineer, I prefer to rely on data. And given that our discussion is technical, the purpose of this lecture is to give you a brief overview of what the data say. And it's a bit complicated because we don't have long observations. Because monitoring is a relatively recent activity. Okay, and if you look at monitoring of waves, because we are interested, for instance, in ocean weather, we started, as I said, in 1950. So observations are very limited in time. Okay, good. This lecture contains a discussion on, first of all, to give an idea, a discussion of data and also a discussion of models. So first of all, there are some pictures, and let's focus on warming first of all, because it's easy to start from warming, because warming is something that is more evident. Anybody agrees that we are in a period of warming, and warming is testified first of all by the regression of glaciers. You can find on the web several pictures, glaciers photographed in 1900. This is in, if I remember, it's It's at the Svalbard Island. So this is 1900, this is 1960, and this is 2015. So you see a big difference. It's striking. There is no doubt that glaciers are retiring. And this retire started around 1750, 1800. The fact that the retirement, keep in mind that global warming, usually we assume that it starts from the Industrial Revolution, because before the Industrial Revolution, CO2 emissions didn't increase much. The Industrial Revolution marked the increase of CO2 emissions, because they needed steam power, and therefore they started burning coal for producing heat, steam power. And it was a big jump. So this is why we locate the beginning of the modern era and the global warming around 1860, but we will see at some graphs there has been a marked increase of temperature from 1990 to today. And therefore, we are usually, when we say 1960, in 1960 there was not really a big concern of warming. At that time, there was a concern about cooling, because around 1970 there was a decrease of global temperature, and therefore people were concerned by another glaciation. And then in the 80s, temperature started to increase again. But still, you see that there is a huge difference from in the past 50 years, which testifies that the Earth is warming. Now, big question, how much is warming? Because it's not clear to the public. Because we listen to people sometimes saying it's clear that it's warmer. 10 years ago it was not so warm. Or you listen from elder people, they typically say, when I was young, 50 years ago, it was much colder. We had a lot of snow, they say, much more than today. So, but when we get to the point of saying how much warmer, it's not clear. So let's look at some graphs. And this is global temperature. This is a graph from 1880, so starting of the Industrial Revolution to 2020. It looks like a sharp increase, but let's look at the details. First of all, the vertical scale. We start from, this is, 0 is the global average, it's the overall average during this period, okay? And we go from minus 0.2 with a minimum of minus 0.4 to plus 0.8, more or less, let's say plus 1. So we are talking about plus 1 plus 1.5 degrees. It is something that cannot be perceived by your skin. So it's really not really reliable when people say it's much warmer, because a difference of 1 degree, you can try in your car to raise the temperature 1 degree, is something that you can hardly perceive. A glacier perceives it. It justifies a retreat of hundreds of meters for a glacier, but for a human, it's hard to perceive. There is to say that this increase is a global average, and it's not uniformly distributed, so there are hot spots where temperature increase like 3 degrees. If we talk about 3 degrees, it's something that we can start perceiving. If we increase the temperature in our house from 20 to 23, we clearly perceive it. If we increase from 20 to 21, it's not really so evident. Here you see individual measurements every year and a moving average. It's a 5-year moving average. First, look at this period of global cooling. Okay, and this is the period that I was mentioning before. From 1940 to 1950, look at the sharp decrease, about 0.2 degrees, and this was clearly perceived. And there were difficult weather conditions during that period. Okay, and then look at what happened recently. From 1990 to 2000, let's say around 1990 it was still quite constant. From 1990 to 2000 there was a sharp increase. There was a hiatus from 2000 to 2014, this region here. And this originated a lot of discussions, a lot of research questions, because in 2000, after the sharp increase from 1990, the prediction of climate models was a very sharp increase in the next 10 years, while in the next 10 years they had like a stabilization. In the past 5 years, there was again a market increase. Last year was not so bad. This, I think, is 2017, not 2018. Was not so bad, but 14, and I think it was 14, 15, 16, there was a sharp increase. It was just 3-point increase. And then it was stable in 2017. 2018 was again, I think it was a bit lower than 2017. It's not clear what will happen in the near future, of course. Overall, if we look at this progress, it's not something that is really concerning, meaning that even if the predictions now are plus 2 by 2100. The prediction of climate models to 2100 are like plus 1 degree with respect to today, the optimistic prediction. They say if we reduce CO2 emission, we may contain the warming to plus, with respect to pre-industrial period, plus 1.5. This is the target of Paris. You listen newspapers saying the target of plus 1.5. It means that given that now we are at about plus 1, an optimistic prediction is plus from today 0.5. They turned it to plus 2 recently, but they say that if we don't reduce the emission, we can easily get to plus 3, which means plus 2 from today. Overall, even a plus 2, it's not so concerning. I mean, we are more concerned about by cooling than warming, because warming usually implies prosperity. Cooling implies several problems. But what is the concern? The concern is that we may experience a tipping point of the climate system. The tipping point means that if you pass a given threshold, whose position we don't know, then it may be impossible to come back. And we might have an exponential change. These are hypotheses, which are, I mean, they are well motivated, because the concern is well motivated, because indeed we don't know if the climate system has tipping points or not. We know that in the past temperature was much, much higher. If we go back to 6 million years ago, we know that on the Earth there were plus 5 with respect to today. So the planet would survive. But at that time, life was present with a very different behavior. We don't know if modern society may survive to a plus 5. And therefore, you know, the concern is motivated, because, you know, even we don't know if the system may, at a certain point, explode in a way. On the other hand, we should be clear in saying that this is a concern, it's not a certainty. So, as engineers, we also have to make clear what is uncertainty. So, if I look at the data for temperature, the data speaks quite clearly and say that we are talking about plus 1, plus 2, etc. If I look at the models say that we may experience a tipping point. So, okay, this is for temperature, and here there is a long discussion. I suggest you to read this lecture, because I believe it provides an objective overview of what we know and what we don't know. So the discussion is also focusing on the uncertainty, etc. And I don't want to explain to you line by line what's written there, because it's easy to read. So I ask for your independence and autonomous study in this, especially because at the exam, you know, I may ask you what is the order of magnitude of climate change, but I don't go into the details. I'm not asking questions that require you to give a description, to give so this is something to read and to memorize in its big picture, not in the details. So I suggest you to read it, but don't be concerned because at the exam you can easily respond to what I'm asking. Then, in order to justify this graph and to comment this graph, I am including a picture that goes back in millions, hundreds of millions of years ago, where you can see the changes of temperature of the Earth and its related temperature to concentration of isotopes, and this explains the progress of glaciations. So we had several glaciations. One thing that people don't know is that today we are in a cold period. So this is today. If we go back, you see, 100 millions of years ago, we had a hot period where the temperature was much higher than today. And therefore, we are in a cold period, but still, in this cold period, now we are experiencing a warming. But this explains that climate has been always changing. What is the reason for these glaciations? Maybe a meteorite impact that changed the inclination of the Earth axis. Maybe that there was volcanic eruptions, a very violent volcanic eruption that obscured the atmosphere. There might be several other reasons. If you look at the reasons, motivations for the extinction of the dinosaurs, you see that these are the motivations, an impact from a meteorite, etc. And it seems something that is not, looks unlikely to us, but actually it's not. If you look at the history of humans, I think, if I'm not wrong, humans defined as we intended them, started their experience on the Earth like 5 million years ago. 5 million years ago, and history documents what happened since 3,000 years ago. 3,000 years ago is like in the history of Earth, look at this graph that extends to about 500 million, 3,000 years, which is our historic memory. It's like a 1 second in the history of Earth. So what we can report since 3,000 years ago is nothing. If we look at the surface of Mars, for instance, we see big craters. Why do we see these big craters on Mars, which are given by meteorite impacts? But they are very large. I mean, meteorites can be large as the moon. And on Mars, you see indeed craters that are like hundreds of kilometers large. And we can see them because on Mars, water disappeared hundreds of millions of years ago. And therefore, there is nothing that models the surface. So Mars is, if we look at Mars, is a clear demonstration of what can happen to a planet in the course of hundreds of millions of years. The Earth is not a clear demonstration because the Earth is modeled. So if in the past 5 million of years we didn't have any impact with the meteorites, it doesn't mean that in the next 1 million of years it may happen. And of course, if we had impacts before than that, they are cancelled by the modeling action of water. But it may happen that the Earth is impacted by a meteorite, which can cause the extinction of life. It may happen because, you know, if Earth is displaced somewhere else by an impact, of course, life wouldn't survive to it. So, I mean, it's an important issue to keep in mind that in nature, in the natural establishment of things, very huge changes can happen. And of course, we are not concerned because we see these changes as unlikely. But actually, they are unlikely in the short term. Okay, we may think that humans will survive on the Earth for how long yet, maybe not much, because, I mean, may survive like 20 millions of years and not more. First of all, the human extinction will happen, of course, we know that, because for many reasons. So we may say it's unlikely that in the next 20 millions of years we experience a meteorite impact, but it's not impossible. And therefore we have to think that, today we have the feeling that we can control everything. Actually it's not. There are, okay. So this is, just to put into the context, this is a recent temperature, recent progress of temperature from 0 to 2000. It's important, this graph, because it explains to you that we had a period of warming in the Middle Age. It's called the medieval warming period. It's not clear if it was global or not, but there are several reconstruction and witnesses that prove that in the Middle Age the temperature was higher than today. Okay, because it's natural variability. This picture, you already saw it, clarifies with respect to the Po River that there are cycles, natural cycles in meteorological variables, and these cycles cannot be explained. These cycles have different periods. There are oscillations, and this is to clarify the role of what is called the natural variability. So we have a human impact, we have a natural variability. Still, as engineers, let me say that we may not care about the origin of the change. We just need to care about the change, the magnitude. So this is why I'm looking at data. I show you the magnitude of changes. So we already clarified for temperature, +1. And we can not bother about the origin as engineers. Of course, we have to make a prediction for the future, but the lifetime of our infrastructure is 100 years, so it is not a long-term prediction. Okay, here there is a discussion on the human influence on climate, and it's a detailed discussion of what I already mentioned, greenhouse effect, and etc. Discussion about climate models. Now let's look at precipitation. Precipitation is a first important issue for us, because it's related to fresh water flow in coastal area. We need, of course, to know what is the dynamic of sea level, but also we need to rely on fresh water flow. So, what is this graph? It's long-term mean precipitation by month. This clarifies, it's not a change, clarifies how precipitation is distributed over the Earth depending on the months, and is averaged in the long term. Long term for precipitation means like 100 years. And where it's dark blue, it's more precipitation. And it reflects what we know. Where it's green is low precipitation. You see, for comparison, that Italy is about green and blue. Actually, average precipitation over the Earth, over the globe, is about 1 meter. Keep it in mind, orders of magnitude are important. Over Italy, it's more or less the same. Over Italy, average precipitation is ranging from 2.5 meters in the Friuli region, down to 600 millimeters in Sicily. So this is the variability. The average precipitation of Italy is about 900 millimeters, which means that in Italy we have almost the same average precipitation of the globe. And you see that there are countries where we don't have much precipitation, and around the equator, in the tropics, we have amount of precipitation that may reach 3 meters, 4 meters per year. So keep in mind the orders of magnitude. Where you have less than 300 millimeters, it means generally water scarcity. The distribution of rainfall and the distribution of water has a strong influence on the distribution of people, of course. If you look in the Sahel, you see white. White is low precipitation. Okay, now, is precipitation increasing, decreasing, stable? If we look at the average, it's at the global average, it's about stable. There are still some changes depending on the region. So there are places where precipitation increased and places where precipitation decreased. I think there is a graph around here, let me see. No, not yet. And actually, what we noticed is that indeed there is a tendency of precipitation to increase where it's already high. So the wet gets wetter, the dry gets drier. This is a pessimistic say, which it's indeed reflected on what we observe. There are not big changes. Usually they are contained, I'm talking about average rainfall, within plus minus 20%, and 20% is already a huge change with respect to the long-term average. So keep in mind this order of magnitude. When we talk about precipitation, plus minus 20% is the range of change at the global level. And as I said, the global average is about stable. Extreme precipitation, so this is the progress of frequency of extreme precipitation event over the global surface and northern hemisphere. What we found, this is a study that I completed with a colleague working in Canada, and it's based on daily rainfall. So we are talking about daily. What we found is that this is a percentage increase, this is an increase in the number of events. And so there is a change that is about, even here, plus 10% in terms of number of events. If you look at the magnitude, it's not reported here, if you look at the magnitude of precipitation, it's not extreme precipitation, daily precipitation is not much increased.